It's work with a former postdoc, Duncan Hewitt, who foolishly went back to Cambridge, and a visiting PhD student, Giordano Ponetti. Okay, so I'll kick off with layering in slots, but I should explain sort of how I'm approaching this particular problem. So I'm not an aficionado of all of this doubly diffusive layering business, but I thought I'd like to get in on the act. And then I started thinking about it in the context of porous medium, because Duncan Hewitt did his PhD on thermal convection in porous medium. And so I thought, well, maybe we'll add a bit of salt, sprinkle a bit of salt in there, see what happens, see if we can see a transition to something that starts to layer. So that was kind of the background, but it's all going to be 2D. So it might all be completely spurious, but it's a proper slot, perhaps. So the usual kinds of equations for porous media. So you replace the momentum equations and the Navier-Stokes equations by Darcy's law. So I've quoted the equations here in dimensionless form. So we've got Darcy's law in terms of a stream function, T and S, as salt and heat. And we've got the heat equation and the salt equation. In a porous medium, you have a prefactor there, which is to do with the fact that you in principle have heat transfer through the porous medium, whereas you wouldn't get salt transfer through the porous medium, so that accounts for that. But in practice, I'm just going to set this coefficient to 1. That would be relevant if you had a Healy-Shaw cell. Okay, so we've got a couple of parameters that we've seen several times already. There's a Rayleigh number and this density ratio, and a diffusivity ratio, a Lewis number. Okay, so I'm going to be doing two-dimensional incompressible fluid in this Healy-Shaw cell, or you might think of it as a porous medium. There's one assumption that you need to make, which is that the flow length scales, so for example finger widths, which are normally quite small, they have to be much larger than the slot pore scale here for this to be a valid model. There are some motivations that you might be interested in. People talk about this kind of a model in the context of geothermal systems or magmatic systems. The stability characteristics, the linear stability characteristics of this system are very similar to normal doubly diffusive convection. Okay, so let me just show you some of Duncan's results for thermal convection. So that problem was motivated by carbon dioxide sequestration, and I'll show you some simulations. And so there's a sample simulation here, and then there's some statistics that's been extracted from a series of these computations. It's the wave number of some large-scale pattern that's observed as a function of the Rayleigh number.
Which quantity are we looking at?
So this is temperature in some funny color scheme. Here's a movie of it. Yeah, this is coming down, this is going up. Right. I don't know why he chose that color scheme, actually. Anyway, so the main dynamics that they see is that there's eruption of small plumes from a boundary layer at the top and the bottom, and they swept into this much larger scale columnar type of convection. Let's do it again. So that's what it looks like. Now, this is what they observe for a very wide range of Rayleigh numbers. Let me just, let me quickly contrast that with what you see for normal Rayleigh-Benard type 2D convection. So this is actually an infinite Prandtl number simulation, but it's characteristic of what 2D Rayleigh-Benard convection looks like at these kinds of Rayleigh numbers. So you don't see this sort of large-scale columnar pattern. You see these erupting plumes. That's the sort of thing that you're probably quite familiar with. Okay, so Duncan sees this in this porous medium. Okay, so the broad motivation for this first part of my talk is to sort of sprinkle salt on this and see what happens. How does this state transition to something that might layer? That was kind of our original goal. And you might say, well, okay, to see layering, all you need to do is this. Okay? but let's call that elevating. All right, so the scaling law that's evident here for the wave number of this pattern as a function of the Rayleigh number, that comes from the following argument. So if you just imagine that you have a periodic domain, these elevator solutions, you can tune them to be exact nonlinear solutions, and they suffer a secondary instability like that. Okay, so this is kind of reminiscent of some of the things we've already been seeing. Okay, so the argument that Duncan made was that if you have a finite domain, as in this case, this is some sort of a convective instability. So if the time scale for growth is less than the time it takes for the secondary instability to be swept across the domain, then you will see a persistent columnar state of that form. And then if you look at the nonlinear solution, you look at the secondary instability of it, you can then come up with a scaling law, which is that the wave number is the Rayleigh number to the 5/14ths. And that matches very well with their numerical simulations. Okay, so that's kind of the background story of this porous media problem. So here we go. Now let's add some salt. So we sprinkle in salt. We've added a stable salt gradient, and this is a finite domain. We're fixing the heat and the salt at the top. Right, so this is stabilizing salt, destabilizing temperature. The top figure here, that's showing you the Nusselt number, the heat Nusselt number against the density ratio. So this is a measure of the strength of the salt. So what happens is for different Lewis numbers here, different diffusivity ratios, to begin with, some of them actually have slightly higher heat transport, but then eventually the salt kills everything. That's largely what's going on. Here are some patterns of the salt and the temperature for simulations. This is increasing density ratio, so as you're marching along here. But, you know, roughly speaking, the patterns don't change too much. They sort of weaken because the salt is stabilizing the convection. And for the small Lewis numbers that we're dealing with here, you see this sort of smaller scale structure in the salt field. But by and large, these columnar type states, they stick around.
So the density ratio is defined the same way as in normal Dublin physics system, in the sense that if it's smaller than 1, you're still convectively unstable in terms of the density, and if it's bigger than 1, it's density stable.
So my density ratio is exactly what you're familiar with, right?
So the first 3 is still, the density still increases upwards. The last one, then the background density decreases upwards. Is that correct?
That's right, yes.
So it does sort of look a bit different from the last one.
That's right. But it's largely looking different here. The color maps are not the same, and it's just by the time you get to here, it's almost a much more laminar state. And in fact, if you go any further than this, you just see kind of regular traveling waves. You get sort of weakly nonlinear patterns. So it's primarily the stabilization of the convection that you're seeing there. Okay.
Are you talking about that working on in the last 2? Like how you get coming up and then looking at?
Well, so there's some you can kind of see it a little bit more in the bottom pictures here, but I didn't want to describe those, as I decided to talk about part 3 later. Bruce permitting. And it's, yeah, so the things weaken, and then there's a possibility that the scale is changing too. And so maybe this is characteristic of when the scale of the convection pattern is changing. Okay, so let me just go back and remind you a little bit about diffusive layering. So I don't really need to say much about this. This is pictures taken from Miroux et al. So that the folklore, according to some, is that there's a linear instability. At some point it saturates because there's a secondary instability that's generated. The kind of state that's been generated then sort of collapses into a bit of a mess out of which layers evolve. All right? Linear instability, secondary instability throttles it, there's a mess, the magic happens, layers appear. You can discuss that later. All right. So, okay, so that was in a periodic box. So what happens when we try and put this porous media problem in a periodic box? So unfortunately, when we do that, this is for these parameter settings, what happens is that the thing just breaks. So here we've got the Nusselt number. Again, I'm going to show you lots of plots like this. So we're going to have the salt, the temperature. This is the mean, the horizontal averages of these things. We've got the density, the average, horizontally average density profile. And then this is going to be the Nusselt numbers. There's a salt Nusselt number and a temperature Nusselt number. And that's what's going to be plotted in here. I can't. As a function of time. Right, sort of an instantaneous Nusselt number pair. Okay, so snapshots, salt and heat, averages, instantaneous Nusselt numbers. So in this case, what happened is, unfortunately, the linear instability grew, it's growing exponentially, and then the simulation just broke. And that funky thing there is the thing breaking.
That's still for density ratio smaller.
I'm sorry?
That's still density ratio smaller.
This is for a density ratio of 0.9. Yep. So, okay, this is what happened most of the time. Right, we were trying to get up to relatively high Rayleigh numbers and so on. We threw in some initial condition, hoping to get the linear instability to saturate through a secondary instability. And in fact, you know, the complicated structures that you see here, that's because the original elevator mode, which is independent of Z, a simple sine wave in X, it's obviously generated smaller scale structures as it's grown. However, it's persisted until it got to such large amplitude that the computation broke. There were some situations where we did actually manage to get the secondary instabilities to saturate. So here we've got a linear instability that's growing. It's growing exponentially. At some point, you'll see secondary features appearing. So that's the secondary instabilities, and they do successfully halt the growth in this particular case. However, what then emerges is something that kind of just looks like it's elevating still. It's a complicated time-dependent state, but it's largely elevating. And you've got these structures that are still largely going up and down. And if you look at the horizontally averaging fields, there's no sign of any kinds of layers. Okay, so this is sort of reminiscent of something that I think Charlie is familiar with in regular thermal convection. So the secondary instabilities here, they either don't saturate the primary instability or they generate a state which doesn't look anything like what you get layers out of.
How big is the box now compared to elevators, scales?
In terms of the elevator scale, so the...
How many elevators per box?
So in this particular case, so for this situation, the most unstable mode is the biggest wave number in the box. So the elevators that grow are the ones with just one wavelength in the box. Okay. Okay. Ooh. So so that was the doubly diffusive version of this. So we thought, well, let's try the fingering version, and let me remind you of Timo Radko and other type of simulations where you have 2D fingers instabilities. They have a secondary instability, and then it layers.
But just to be clear, so you're never really in the double diffusive regime in the sense that you're still fully convectively unstable in your previous one. Have you ever run one where you are at a system that is not convectively unstable?
So one of the differences between porous media and regular thing is that the doubly diffusive regime, it doesn't have this window of oscillatory convection, linear instability, where, well, you can see where I'm going, right? It doesn't have that little window. Okay.
But if you remove the porosity from the previous movies, you wouldn't see layering. Is that right?
I'm not
Don't worry.
I'm not seeing layering anyway. What do you mean?
No. I'm just saying, if you in the previous movies, if you
Yep.
removed the porosity, would you or would you see something similar to what you're showing?
You mean if I use the same parameter settings with regular doubly diffusive convection,
Yes.
would I have seen?
What would you see?
I'm not completely sure. We didn't quite look at matching up the two parameter settings. And the reason for that is that the Rayleigh numbers that you use in a porous medium are very different for similar phenomena than in the 2D Rayleigh-Bernard case. Okay, so we tried the fingering case, and the same thing happened. So this is a case that broke, and there were some situations where you could get the secondary instability to saturate. So here, the most unstable elevator mode has got more wavelengths in the domain, so you see it growing. You see the fingers appearing. They grow. At some point, there are a bunch of secondary instabilities, and then you get a complicated state, which is saturated, and it just continues like that. It's dominated by the biggest elevator in the box, eventually. And there's no signature of any steps in. Okay, so most of the time, the secondary instability, we were unable to get it to control the primary instability, and when it did, the dynamics was still dominated by elevators. Okay, so we thought, well, maybe if you have a finite domain, maybe that helps, because you don't have these linear instabilities that are nonlinear solutions. So we tried that. So this is fingering with fixed boundaries at the top and bottom, fixing heat and salt. And the same thing happens. We get some stabilization now. However, you don't get anything that looks like layering. It just keeps elevating. Now, I should say that we've done a whole bunch of numerical experiments, and this is what we found. We didn't do an exhaustive search throughout parameter space and everything. Okay? I just thought it would be a lot easier to get layers. Okay, well, what about if you start with a layer? So Griffiths, actually, in 1981, he had an experiment where he set up a step and heated it and saw the persistence of a step in the doubly diffusive regime. And actually, that's what we do see. If you start with a step, in the doubly diffusive regime, it excites a lot of motion, but the state is prolonged. So this is certainly consistent with the experimental results of Griffiths. So that was sort of vaguely a success. Everything just collapses if you take the density ratio to be less than 1, or if you look in the fingering regime, you get elevators in that case. So this is a sort of hint that you might be able to get layering. 1.05. Okay, and then we thought, well, what are the common scenarios that people use for layering? Well, you can either try and start with the linear instability. You can initialize it with a step, which is sort of putting the answer in to begin with. Or you could just try the Huppert and Linden style approach, where you take a stratified layer and then you impulsively heat it from the bottom. And so finally, in that case, we observed layering. That started awfully quickly, but so the stratification's been mixed up here. There was an interface that formed, and now you see another mixed layer appearing above it, so you see the generation of steps. So previously, actually, Schuf et al. In '98 had done some computations where they'd seen this, but we couldn't reproduce their numerical results, actually. We tried to reproduce their numerical results, and we couldn't. They actually did some calculations at very, very high Rayleigh numbers, and they had much lower resolution. We couldn't reproduce their results. Anyway, it does seem to be the case that if you go for this particular scenario, you do get layers. Okay, but in general, more often than not, we found that the system just liked to elevate, not layer. Okay, so that's part 1. So now I'm going to talk about part 2. So this is this sort of shear yes?
So the real porous media equations do have a small partial viscosity. It's just usually neglected.
You mean the Brinkman term?
Yeah, the Brinkman term.
Yeah.
If you put that in, does that...
That could help. Yeah, that could certainly help controlling things.
Change it,
It might do. It might do. Yeah. That's certainly a physical addition that you might think would do something. And the issue that we're having here, I want to emphasize this, it's not that the system may not layer. In fact, you know, there are a few instances there where we could get a layer to persist or layers were created. It's just that this linear instability, it just could not be controlled by the secondary instability. That's the key issue. So it couldn't provide this state that could then layer. That seems to be the missing link here. Now, if you added things like the Brinkman term, it could be that you would help the secondary instabilities control the primary instability, and then it might layer.
But it does if it's all Brinkman, right?
Yes, yes, yeah.
But it's actually, sorry, go on.
Did you ever try to calculate the flux ratio and see if it varies with the density ratio?
So we didn't try and diagnose the fluxes or anything like that to check for gamma instability. We didn't try that. Okay. Yeah?
This business, Neil, that it won't saturate the initial instability because you've got a weak perturbation, and then by the time that's got big enough, your elevator is huge.
Yes, that's the problem.
Yeah, but you've got the size of the initial perturbation at your disposal.
Yeah, so you tickle it at different amplitudes.
But it would grow to a sizable amplitude before your elevator has grown to get out.
Oh, you mean the amplitude of the secondary mode? We didn't try tickling it that differently. These things are initialized with some sense of random noise, so it's out of the noise that the modes are growing. Yeah, yeah. So we didn't explore that a little bit. I should say that in the work that Charlie did with Rayleigh Bernard, then what happened was that you did sort of end up with sort of secondary instabilities, kind of like you were saying, but it was all numerical. So there's some issues about calculating the numerical solutions. It's not clear that you're actually looking at a genuine solution of the equations here, because the elevators are just getting too big. Okay, so part two. So this stratified shear instability. So it goes back to some classical type of shear instability from our forefathers. Okay, so I'm going to be thinking about a staircase with shear. Okay, so this is a bit like what Bruce was talking about yesterday. So I'm going to have a number of steps, and I'm just going to put in a linear shear flow on top of that. Okay, so that's the sort of the vision of the linear stability problem that I'm going to be thinking about. So I'm going to have equally spaced steps of equal size. All right, so there's not going to be any inhomogeneity in the staircase that might give rise to some kind of localization effects or anything like that. I'm thinking about this as an instability problem. So when you have shear and stratification, sometimes people like to interpret the instabilities in terms of interacting waves. So for example, if you have vorticity interfaces, like in Rayleigh's classical kinds of broken line profiles, you can have vorticity waves interacting, and that's how people like to interpret the Kelvin-Helmholtz instability. If you have a density interface interacting with a vorticity interface, that gives rise to what people call the Holmboe instability. And then there's this third case where you have two density interfaces with gravity waves riding on them interacting. That's the Taylor-Caulfield instability. We had a couple of margaritas last night, and afterwards I changed some of my slides. So you'll see that momentarily. Okay, so that's the basic setting.
The density gradient's unstable.
Oh, I got it the wrong way around. Sorry. That's my. Okay, so before I go on about the staircase, let me just show you what happens with the single Taylor Caulfield instability. So this is going to be some measure of the amplitude of the instability wave. So here is the buoyancy profile. That's what I was trying to plot, not the density. Okay, so minus the density. So we've got a step here, a step here. We've smoothed them in the numerical scheme. And this is showing the buoyancy field, minus the density field. So this is what happens. You basically, these waves growing on the interface, and they basically break to form what you might call a Taylor billow. So there's a layer here, right, or a step here, a step here. What happens is that the wave grows, and the step structure becomes billow-like.
Is that 2D?
This is 2D. Everything in my talk is 2D. So that's what this. Sorry? I take it that wasn't a serious comment. Okay, so that's what happens with just two interfaces. So, okay, what happens if you have more interfaces? Well, this is with two interfaces. So 2 interfaces, 4 interfaces, 6 interfaces, and you can keep on going. So what's plotted here is the horizontal wave number against J. That's a stratification parameter. It's a local Richardson number. Okay, and so this band here is a band of instability that you get with 2 interfaces, and that's what I showed you on the previous slide. So as you increase the number of steps, then you increase the number of these bands. And basically what's happening is that you've got these gravity waves riding on these interfaces. They get Doppler shifted by the basic shear flow, and when their resulting phase speed matches up between 2 interfaces, there's a resonance which leads to an instability band. So you can imagine that you have a large number of interfaces. You can just Doppler shift hundreds of these gravity waves to be into resonance to lead you to all of these bands.
Those bands are all infinitesimally thin, except maybe the bottom, is that right?
They are thin. They're not infinitesimally thin.
Okay.
Yeah, but they're yes. So you can see the thickness of the bottom one. You can't see the thickness of these ones. Okay. Now let me just interpret them a little bit more. So the band down here, there's actually multiple bands there, and that's when you're Doppler shifting the nearest neighbor gravity waves, and they are somehow the strongest resonances. Right, so you can imagine that depending upon the number of interfaces, there's many bands down here that overlap. And the reason why they overlap is that you feel your nearest neighbor, the next nearest neighbor is further away and you don't really feel them, so all of the nearest neighbors' interactions, they all look roughly the same. And then you've got the next nearest neighbor, third nearest neighbors, and so on. So this is the kind of the structure that you can get. And there's a linear stability problem with here, and you can go to town looking at the mathematical structure of it. You can write it all in terms of your favorite types of matrices, and you can go to town on your matrices like Bruce did. I thought I'd spare you that. Okay, so here we go. You've got all of these instabilities. You've got overlapping bands. But the strongest nearest neighbor interaction is that one. Okay, so what happens? So this is what happens when you have 4 steps. So now you've got your 4 steps, and I'm not going to show you a movie, I'll just show you what happens. So in this particular case, you've got these nearest neighbor interactions, so you expect an interaction between 2 waves here, 2 waves here, and 2 waves there. Right, they're all unstable at this particular parameter setting, and you see these waves growing, and what happens is that these waves interact and they distort the layer structure here, and it forms these billows, and you get 3 stacked billows.
The color is shear, right?
This color is this is density gradient actually.
Oh, okay.
This is density gradient. It's so there's no the way that there's no perturbation vorticity to begin with. But as it evolves, it looks like this. So the vorticity is somewhat like this, but this is the density gradient. And the reason why I'm plotting you the density gradient is that when we did this is a nonlinear computation, but we made use of a particular reduction of the equations to simplify the model a little bit. And there's one main variable that comes into that particular problem, which is the density gradient. So there's a main variable, and that's what's plotted. Okay, so the main thing here is that you get these stacked billows. The steppy structure disappears. You get these billows here. And in this particular computation, they slowly damped away by viscosity. If you put more waves in the horizontal, they actually coarsen to give you the largest scale billow in the horizontal. However, you still see these stacked billows in the vertical. Okay, so let me just sum up with what I've told you about there. Okay, so I've got okay. Okay, so So we had great difficulty in getting the primary instability to saturate in this porous medium problem, and as a result, we could not find any layering. So my second part of the problem is that you can formulate this nice stratified shear instability problem. If you have a staircase structure in the density, then in principle it's susceptible to a large number of these Taylor-Caulfield instabilities. So it makes you wonder whether this could be relevant in the evolution of a staircase. Okay, now I have lots of time. Well, questions about that?
But your last bullet point here would imply that it all goes to coarsening. So if we have a staircase and you know, these types of instabilities.
Well, if they would operate, then instead of getting this horizontally homogeneous staircase, they would roll up, and you would get you would see horizontal variations, and you wouldn't be able to necessarily identify an interface anymore. Okay, you would actually see these sort of billow-like structures. Okay, so you do not see that, right, in ocean observations. So either there's no shear, or for some reason this instability is inoperable.
But the thing is, there's always shear.
Yeah.
So,
Well, so
yeah.
what's going on?
And it's inertial waves,
Yeah.
No, but
they're
there's
all different directions.
no, there's vertical shear
So it certainly
associated
is,
with
Yeah.
geostrophic shear.
Yes, and the layers I talked about in the tropical Atlantic, they're on the edge of the subtropical gyre, and there's a
Right.
media geostrophic shear,
Right.
This is fascinating.
Maybe the
Yeah.
issue is that you have uniform shear everywhere, as
That's
opposed
right.
to having shear where you've got the steps and more or less uniform velocity in the layers.
We haven't looked at what happens if you try different shear flow profiles. But I don't think that makes much of a difference. All you need is some shear of some kind to Doppler shift these gravity waves so that you can bring them into resonance to get these Taylor instability modes, Taylor-Caulfield.
I don't think you get the Taylor cauliflower mode if the shear is at the same point
Well,
as the
it's-
density.
yes.
Right, right. So
Yeah, maybe.
you get something more like
Right.
Kelvin.
Right.
But there are regions where you see thicker layers and thinner layers,
Yeah.
and how those regions relate to the background geostrophic shear, I think would be something kind of interesting.
Yeah, I mean, it's all 2D as well. You should be wary of that.
But presumably these calculations at very modest dimensionality, and that really modest Reynolds number, I guess, would actually transition if you were at high enough.
Yeah,
Reynolds number.
yeah, right.
And
This
that
is
would
the-
be more interesting.
Yeah. So this is actually an attempt, because of this particular way that you reduce the problem, you can try to do an inviscid computation.
Yes.
Okay, but for sure,
But the secondaries would be three-dimensional.
Yeah,
that would
right,
drive the cascades.
right. Yeah.
That's very.
Yeah.
Isn't this the setup that Nick just told us about, but he didn't see any of these Taylor Yeah, isn't it the same? I mean, those shear bands,
Well, I maybe if you,
steps, and where's Nick?
I'm over here.
I mean, there is this funny kind of instability band structure. Yeah.
Nick, that if you picked a different value of things, or the Reynolds number was a little higher or something, it would break up? Do you have a good feeling for that?
So actually, I didn't point out here. So the growth rates here, as you go up these bands, they get much smaller because you're further and further away. So if you had a relatively high stratification, you might have lots of these bands, but they would be centered around very specific wave numbers, and their growth rates wouldn't be particularly large. So any damping in a code might not see them. It's only when you get down here that you get a relatively strong instability, which is at relatively small stratifications.
Part three?
Hmm?
Should we go to part three? So you
Part 3.
We do have velocity profiles through the steps, and they tend to be slabs,
Yeah.
because the convection is,
Right. Yeah.
enough vertical mixing there that
Yeah.
you gotta, it's all the one direction here, one direction, the next layer, another direction, the other.
Yeah. Pascal?
So you start right now with the density profile where the density is still ever so slightly stably stratified in the layers, right?
Yep.
most of the diffusive layers that we see are actually convective in the layers.
Yep.
Ever so slightly
Yep.
convective. Would that change a lot your picture?
Um,
In the sense that maybe the gravity waves don't have this opportunity to talk to each other as much because they're evanescent.
yeah, perhaps.
And so the second part of my question, which could be very interesting, is that in one of the problems we've had.
Well, actually, even in this case, I've got a flat density there, so they are decaying exponentially between the interfaces. Yeah, so that wouldn't make that much of a difference anyway. Sorry, carry on.
And then so in a lot of the simulations that we have, we see that in certain parameter regimes, we see that the convection in between the layers excites very strong waves on the interface, which then look like the amplifying amplitude and then perhaps cause these kind of mixing events. So it looks like there's a positive feedback between the convection and the interfacial gravity waves, which then could actually
Yeah.
rise to the sensibility. So my question is, if you have a simulation, how would you diagnose the instability? Could you? Is there a way of smartly massaging the data to see if it's there?
Well, it's really, this instability is a resonance one. So I guess I'd look for the signature of that resonance. So you detune it slightly, you ought to see waves that are almost at the same phase speed, but they aren't. Then you tune it to resonance, and then they lock on and become unstable.
I don't know if we can control the way
Yeah,
it comes out.
yeah. Yeah, I don't know. Let me just briefly mention part 3. So I probably should have talked about part 3, because this is all about layering, and so far we've actually talked largely about double diffusion, right? So rheometry. So in rheometry, when you have a complicated fluid, you have something like 2 plates. You spin the top plate, or you have a plate and a cone. You put the fluid between these things. You measure, for example, the torque as a function of the rotation rate. And that allows you to build up a cartoon of the material behavior of non-Newtonian fluids. And the cartoon is usually portrayed as this picture where you have shear rate against shear stress. So, straight line through the origin, slope viscosity, that's the Newtonian fluid. And then if you have a non-Newtonian fluid, the picture's different, and people try and catalogue the behavior of non-Newtonian fluids in terms of this kind of a cartoon that people affectionately call the flow curve. So we're talking about materials like this, okay? That's because there's a sand skipper living on the mud, and mud is non-Newtonian. And the snail, it's the mucus underneath the snail, that's non-Newtonian. Okay, so here's some actual experimental data for this stuff, which is hair gel. So you've got a flow curve that does something like that, right? So the Newtonian behavior is a straight line through the origin. This is a semi-log plot, okay? But what hair gel does, for example, is it has an intercept and then it has a nonlinear curve here. So the intercept corresponds to the fact that it's got a yield stress. You have to push it hard enough to get it to move. And once it's flowing, the viscosity varies with the rate of deformation, the shear rate. So that's characteristics of these kinds of materials. Okay, so it's all about measuring something that maybe looks like that. There's the interface, there's the yield stress, and then there's the nonlinear viscosity. So that's the cartoon that people like to draw for these types of materials. And that's been the paradigm for 100 years or something. However, recently the rheometry that people have been doing has improved dramatically, and people have realized that this kind of behavior is very, very idealized. And real materials don't do this at all. And one of the things that people have observed, which is relevant here, is that this flow curve appears in some situations to do this, or to do this. So you've got stress against deformation rate, and the steady state flow curves that people interpret do something like this. And the interpretation is that if you have a negative slope here, it's like having negative viscosity, it's an unstable situation. So those are kind of unstable branches. And what people do in rheometry is they either fix the shear rate or they fix the shear stress. So if you come along and you say, I'm going to fix this shear stress, or if I fix this shear rate, then you have a sample in your rheometer that's got this unstable material behavior. And what happens when you actually do the measurement, say in this particular situation or that one, is that instead of observing this, you end up with a flow curve that does something more like that. And similarly here, you would see something that looks like this. A bit like a Maxwell equal area construction. Okay? And, okay, so that's what you observe. You're not kind of seeing this steady state flow curve anymore, this unstable behavior. So people actually try to interpret this a little bit more by going to the rheometer. So the rheometer is normally quite small. It's this $100,000 device that you really don't want to touch. However, people decide that, well, we really need to see what's going on inside the sample, so you get rid of the bottom, you put a transparent plate in there, then you seed the fluid with particles and you do PIV through the bottom. And when you do that, you can actually build up what the actual rotation rate is inside the sample. And so what you find out in these situations is that there is shear banding. So in this branch up there, what you would find is, because it's a very small device, you find that the velocity profile is a simple shear up here, but over these kinds of regimes, what happens is that it breaks up and you get regimes where part of the material, in this case, for example, is not moving at all, and another part of the material is moving. So you've got this shear band here. So what's happened is that the material has been intrinsically unstable, and it's become spatially inhomogeneous in order to counter the fact that you've been trying to set conditions that would otherwise make it unstable. Okay, so people have observed this kind of layering phenomenon. Okay, so it's layering in the context of stress against deformation rate. And it's a very robust phenomenon that people have seen for all sorts of different materials now. Okay, so that's part 3. Any questions on that? Yeah?
So have you
The consequences of this is that